back to the end of week one already of differential equations. So we had that unexpected cold day yesterday. So hopefully you've watched the video where we finish up talking about the section 1-2 stuff. And I do want to make a quick remark that you got the test 0, which is basically your background information sheet. Take home 1 and test 1. These are all due next Wednesday by the start of class. And take home 1 and test 1, that's completely, welcome in Tim, this is completely over the section 1.2 stuff, right? So it doesn't do anything with anything that we're doing today is not on these things. You just want to focus on the 1.2 stuff. In fact, one of the things we do, we'll talk about today is you'll be checking your answer to what we do today on the take home and the test. So that's due next Wednesday. As always, feel free to email me questions or pop in before class with questions or stick around after class with questions if you have any questions on that. Okay, so basically we talked about in the video, we talked about what is a linear equation. This is what a linear differential equation is, and we'll talk more about the bigger concept of linear as we move through things and what that means for us. And then if you're in linear algebra, I think there's a fair overlap between this course and linear this semester. You can think about what that means there. But basically a first order linear equation looks like y prime plus p of xy equals f of x. So you get the y prime, the coefficient of 1. The coefficient of y depends on x, and then we have some f of x over here. And the key to solving these equations is this identity, which is the last thing that they talked about on the video from last year. So here's what we're going to do. If you notice, if we let mu of x equal this integral, then what we've got here is we've got the derivative of y times mu is equal to mu y prime plus p of x mu y. And so this is the left-hand side if I take this and multiply by mu, and then to keep the equality I can multiply that by mu, then that's going to turn the left-hand side of this equation into an exact differential. So that's how we solve these linear equations, is we make use of what's called an integrating factor. So integrating, the reason why this is called an integrating factor, it's called a factor because we're going to multiply the equation. And it's called an integrating factor because it's going to turn the left-hand side into an exact differential, which we can integrate. So this is basically the generic method we're going to be using here. We're going to put the equation into the standard form, and I'm going to calculate e to the integral p of x dx. We're going to multiply both sides of the equation by this factor. That's going to turn the left-hand side into an exact differential. And then I can undo the derivative by integrating. So there I've undone the derivative. Now I can get y by itself, which is the whole point of the differential equation. Now we get this thing over here, which, I mean, you could certainly memorize this formula, but I think it's better just to work through the procedure each time. And so this leads us to the steps in solving a first order linear ODE. First step, make sure you write the differential equation into the standard form. Identify your integrating factor. Since it's a factor, you want to multiply both sides by the factor. Integrate both sides, which you'll be able to do. And then you want to solve for y. So let's do a couple examples here. We got y prime minus 3y is 0. First off, we want to check, is it in the form y prime plus p of xy equal f of x? What would be the p of x here, folks? And what would be the f of x? Because I do have the y prime all by itself. So what's the p of x here? And what's the f of x? P of x is -3, perfect. The f of x is the identity 0. So we are a linear equation. We are in the standard form. So we're going to calculate now the integrating factor, mu of x, e to the integral p of x dx, e to the integral -3 dx, and we get e to the minus 3x. Now you might be thinking, wait a minute, Stitzy, you forgot your constant. So we're going to take we're going to do this once and only once here to show you why we can suppress the constant of integration. If we did put that constant of integration in there, I could use the properties of the exponential to write it, yeah, exactly like this. And so I could rewrite this e to the constant. This is just some other positive constant. We'll call this a C1. So this is just another positive constant. I'm going to be multiplying both sides of this equation by this. This is just another positive constant that I could just factor out and cancel anyway. You follow? So by adding this constant here, it doesn't help me at all, and it doesn't affect what's happening when I multiply through. It'd be the same as instead of multiplying both sides by e to the minus 3x, I multiply both sides by 11^7 e to the minus 3x. It's not going to affect anything we're doing. So we typically suppress the constant of integration, and so we'll just use this as our integrating factor. So now I got my integrating factor. I multiply, because it's a factor, so we multiply both sides of the equation by the integrating factor. So we would get e to the minus 3x y prime minus 3 e to the minus 3x y equals, in this particular case, I'd be multiplying by 0. And 0 times anything is going to be what? 0. And now you can check the left-hand side is an exact differential. It's the remnants of a product rule. This is the derivative of the integrating factor and the function y. And if this is, when you're first doing these things, I highly encourage you to start with this, because at this step will always, this should always work out to be the derivative of the integrating factor times y. Start here, hit this with the product rule to convince yourself you're getting exactly what's on the left-hand side. So now the only derivative is here. So how do I get rid of the derivative? We take the antiderivative. So here we're taking the antiderivative with respect to x. When you integrate the derivative, they undo each other. So we would get an e to the minus 3xy. Technically, there'd be a constant that pops out over here. When you integrate 0, you get 0 plus technically you get another constant. So we'll call this a C1. We'll call this a C2. But once again, we typically suppress the constant that pops out on the left-hand side, because if we go to solve for y, you've got an arbitrary constant minus an arbitrary constant. We're just going to relabel that as another arbitrary constant. Then I can solve for y by dividing by e to the minus 3x, which is the same as multiplying by e to the positive 3x. Boom, there's your solution. And you can verify that this is the solution by starting with this function and plugging it in and see if it equals 0. So once again, that's how you will verify solutions. And once again, on the take-home and the test that's due next week, due next Wednesday, it's all, when it says to verify the solution, it means to start with the thing I give you and plug it into the DiffyQ and show that it works. You don't need to work backwards and solve it. Okay. That's all we're doing for the first take-home and test. And if you're new to how I do things, you are free to ask questions on the take-homes. If you want to double check things are working, once again, we talked about how we could check our answers on Desmos. We'll do another one of those here in a minute, but you can always check if things aren't working out for you. Okay, so there's that. That's your very first solution of a first-order linear equation. Now let's take a look at the second example here. And of course, this is classic Carl. Here's the first one we did. Here's the second one we did. Right? Spot the difference. The left-hand side is exactly the same. The only thing different is the what? The cat knows. So once again, we check, are we in the standard form? Well, we've got the 1y prime. The p of x, the same as before. The f of x is different now. Instead of equaling 0, it's equal to what? X. So when we go to calculate the integrating factor, notice we're only looking at the left-hand side. So the integrating factor is completely determined by that p of x. So we're going to get the same integrating factor we did before. E to the integral p of x dx. We're going to get the same that we got before. And once again, we suppress the constant of integration in the exponent there. And now we're going to multiply both sides of the differential equation by the integrating factor. But now the right-hand side has a little bit of meat to it. And as promised, the left-hand side is an exact differential of the integrating factor times the function. So this is the only derivative now in the problem. And how do we get rid of the derivative? We integrate. And so the left-hand side is the exact differential, once again, of the integrating factor times the function. And now we look at the right-hand side. And now we're back to calculus 2. How would you integrate this function? Yeah, you could use the parts, or you could use tabular method. Either way, it's going to be fine. So you would do like your u would be like your x, and your du would be your dx. And then your dv is e to the minus 3x dx. Your v is minus a third, e to the minus 3x dx. You got your uv integral v du. If you need a refresher on these sorts of things, thank you. If you need a refresher on these sorts of things, thank you, Zron. Feel free to drop me an email. I can send you videos to help you with this kind of thing. So you get a minus a 1/3 x e to the minus 3x minus the integral of v du. And so I get a minus 1/3 x e to the minus 3x. The minus and the minus would give us a plus. But then we'd have a third times a negative third, so it'd be another minus a ninth. E to the minus 3x plus a constant. So once again, if you have questions or need a review of integration, let me know. I can send you handouts and and whatnots. Okay. Oops. All right. So we've got y equals. I want to keep this up here. So I would have e to the minus 3xy equals. And once again, we'll suppress the constant of the integration we get here because we'll just be lumping it with what we get over here. Minus 1/3 x e to the minus 3x minus 1/9 e to the minus 3x plus a constant. And so to solve for y, we would be dividing both sides by e to the minus 3x, which is the same as multiplying by e to the positive 3x. Once you do that, these would cancel out. So you get a minus 1/3 x minus 1/9, and then you pick up a c e to the positive 3x. Any questions on getting to the final answer here? You see what's happening? One of the most common mistakes students will make is they'll forget about the c over here, and they'll forget this piece. They'll just put a c here and forget that there's an e to the 3x that's going to go onto it because we're dividing an e to the minus 3x over there. But this is extremely important because you notice this was the solution to the diffie-q when we had a 0 there. And this kind of thing will always happen. Okay? If you have, and this is where we get into the next thing here. And we're gonna build upon this in later chapters, but I want to introduce this now. Especially if you're in linear algebra, you're gonna see this kind of structure happening all the time. But before I move on, are we all good with getting to here? Check its standard form, identify the p of x, integrating factor, multiply the factor, integrate, solve. So if you have a diffie-q, first order diffie-q, if the f of x is 0, then this is called a homogeneous differential equation. This is one way they use the word homogeneous in diffie-q. Is that. Now, one thing you notice is that if I just let y equal the function that's always 0, that will automatically work for this. So in this case, the function that's always 0 would be called a trivial solution. Non-zero solutions are called non-trivial. Okay. So in this particular situation, notice here I could let c equal 0, and that would be a solution to that differential equation. All right. But if I let c be non-zero, that's the non-trivial solutions. The one that we just did, we didn't have 0, we had x. If I change that to 0, this is called the associated homogeneous ODE. So we have a non-homogeneous ODE because we have a non-zero function here. The associated homogeneous is when you set it equal to 0. And this solution, as we mentioned, appears in the solution of the non-homogeneous. And we have this theorem, which we're going to talk more about this theorem at the end of next week when we get into existence and uniqueness theorems. But I do want to mention it here, that when you solve a first order linear ODE, the solution is always going to have two parts. It's going to have a YC and a Y. Here is important. And if you're in linear algebra, I know there's at least a couple of you in linear, you're going to see this. So anytime you have a non-homogeneous equation, your solution is going to look like you'll have a generic solution for the associated homogeneous. This is called the complementary solution. And then you'll be adding to it a particular solution. The particular solution will work for the non-homogeneous part, and the complementary solution will have the parameter in it that works for the homogeneous part. And you've actually seen this in a very specialized case. We mentioned this Tuesday. When you integrate that, you're really solving a linear equation. Y prime equals 2x. If you want to be pedantic, you could write this as y prime plus 0 y equals 2x. You get to the x squared part, and then you tack on a what? You tack on a c. Now, why do you tack on a c? Well, mean value theorem says you can, but when you take the derivative of your answer to check it, the derivative of the x squared, that gets you to 2x. That gets you to your f of x, right? Your non-homogeneous part. And when you take the derivative of the constant, that gives you what? 0. So this is like your yc, because the derivative is 0, and this is like your yp. And we'll talk more about this once again next week when we get into the theory. Today I just want to focus on grinding through some examples. So we'll come back to this and talk about the importance of linearity there. But let's check this other example. Okay, so here's another example. We've got 2x y prime minus xy equals y. Y at negative 4 is positive 2. So this is an example. It's a differential equation, but we have a condition. So this once again, this is called an initial condition, and we're saying that when x is negative 4, I want the y to be 2. So if I want to think of this geometrically, this differential equation is telling me about the slopes of a curve. I want a solution curve that goes to the point negative 4, 2. So we'll see how this plays into our calculus here. The first thing we have to do is it linear? And if it is linear, we can check because we got to put it into my standard form. Okay, so we got to get the y prime plus the p of xy equal to f of x. So I got the y prime there. We're going to have to take care of that 2x somehow. We got to get all the y's on one side, so I can subtract that off. So I guess I'm going to have a minus xy minus y equals 0. And so now we're going to have to do some more algebraic machinations here. So we got the 2x y prime, and then I could add, I'll factor the y out of here, minus x minus 1y equals 0. Now to get it into the standard form, I need y prime to have a coefficient of 1, which means what am I going to have to do to this equation, folks? To get it, yeah, I got to divide through by the 2x. Now when we do that, that creates some potentially creates some problems, because you can't divide by what? Yeah, you can't divide by 0. So doing this, now we know that x can't be 0. And we know that for differential equations, a solution has to live on an open interval. So at this stage in the game, we need to make a decision, or, well, we don't need to make it right now. But this is going to split the solutions up. We're going to be looking at an there's a positive solution and a negative solution. And we'll talk about which one we pick here in a minute. But at this point, we do have it in that form, and we're going to assume we're on one of these two intervals so that we're not dividing by 0. And so we can identify our p of x here as minus x minus 1 over 2x. And so to get my integrating factor, I need to have e to the integral of that. Okay, so let's figure out what that's going to be. So how do we integrate minus x minus 1 over 2x? What would be your strategy? How would you get going on this one? Yeah, split it up. So minus x over 2x minus 1 over 2x dx. The first term there, what happens to the x's? They cancel. And I got a minus 1/2 times 1 over x dx. So integrate that. Minus 1/2. And what's the integral of 1 over x? What's that turn into? That's your natural log. Now, notice when you do this, you get an absolute value of x. And then once again, there's a plus c we're going to suppress. We're going to suppress the plus c. But yeah, we get this absolute value of x. So this is another thing where it's, well, we've got to figure out what interval we're working on here to get this to work. So how can we pick? In this particular case, well, we'll leave the absolute value for now. We'll just leave it till the end there. Anyway, this is the exponent for the integrating factor. So we're going to do a little algebra here. Once again, properties of exponents. I can rewrite this as e to the minus 1/2 x, e to the minus 1/2 natural log absolute value x. Yeah, good. So that's, well, not quite, Zeron. Not quite here. So we'll do this here. We'll go through step by step here. So there's that. Now let's talk about how we can simplify this part, because you know from algebra, right? You know that the exponential base e and the natural log are inverse functions, so they will undo each other, right? But in order to do that, we got to get this. We got to get rid of that 1/2. What's the legal way to get rid of this 1/2 in the exponent here? What can I do with that negative 1/2? I can put it up as an exponent inside the log. And now we're good to go, right? Now we can, e to the natural log of whatever is that whatever. And then we get that. Okay? Everyone cool with the algebra there? Now, if you're thinking to yourself, Stitzy, this is differential equations. The differential equation piece appears to be done in the very first step by rewriting the differential equation in the standard form. Everything else seems to be all the stuff that comes before it. There you go. That's exactly how every single calculus course has been. Most of the time, it's mostly algebra. DiffEq is mostly algebra and mostly Calc 2. It's pretty much how this is going to all shake down. Anyway, that's our integrating factor. Okay. So what do we do with the integrating factor? Well, it's called an integrating factor for a reason, because we multiply. So we go back to the DiffEq in the standard form, and we're going to multiply by it. So we got the y prime plus the minus x minus 1 over 2xy equal to 0. Now we're going to multiply both sides by our integrating factor. The left-hand side, when we do that, will turn into the integrating factor times the function. So in this particular case, is what, e to the minus x over 2, or yeah, e to the minus 1/2 x, that's fine. Absolute value x to the minus 1/2 y equals, and once again, we've got a homogeneous equation. When I multiply 0 by that, we're going to get 0. Integrate both sides. e to the minus half x, absolute value x to the minus 1/2 y equals a constant. And so to solve for y, we're going to divide both sides by e to the minus 1/2 x, x to the minus, absolute x to the minus 1/2. Once again, dividing by negative exponents is the same as multiplying by their positive counterparts. So I'm going to get a c, absolute value x to the positive 1/2, e to the positive 1/2 x. Right. And once again, this is going to be valid. So you're going to have one of these answers will be good for x bigger than 0. And the other one will be good for x less than 0. The question is, do we need to pick one of them? And the answer is yes, because if I go back to the original problem, it wasn't just a differential equation I was looking at. I had this initial condition. So once again, y at -4 is 2, means that when x is -4, y should be what? 2. You follow? So this tells me which interval I'm on. The initial condition says, okay, I'm looking at this piece. Because of the initial condition, y at -4 is 2. I'm going to plug that in to my equation. So y equals, oops. So x is -4. Y should be 2. I plug the 2 in there. That's c, absolute value, -4 to the 1/2. Oh, which -1/2? Did I miss something? So when I divide these over, they become the positives. Is that what you're talking about, Zoran, or? Yep, okay. All right, good question, though. We plug the -4 in, and this would be e to the -2, or 1/2, I should say, times -4. So I get 2 equals c times. The absolute value of 4, or -4 is 4 to the 1/2. That's a square root, so that's a 2. And then this would be e to the -2. And so I can then solve for c. So once you get done with the algebra there, what's c going to be? Yeah, e squared. So now I can put that back in. Y equals my c, which is e squared, absolute value x to the 1/2, e to the 1/2 x. And we can start then rewriting this. You got base e. We can add those exponents. The 1/2 power is really the square root. And once again, this is valid for x strictly less than 0. So if you wanted to, you could simplify then the absolute value. Right? You might remember from algebra class. Absolute value x is the opposite of x if x is less than 0. And it's just x if x is bigger than 0. So if you wanted to, you could rewrite it this way. Square root of the opposite of x, e to the 1/2 x plus 2. Okay. Now once again, just to show you, you can check this on Desmos. You fire up the Desmos. You enter your function as a function of x. So call it f of x. And we had the square root of minus x e to the 1/2 x plus 2. We can check the initial condition. When x is -4, y should be what? 2. Boom. There it is. Let's check the differential equation part. Let's type in the left-hand side. So 2x y prime, that's f prime of x, minus x f of x. There's the left-hand side of the differential equation. Let's type in y f of x. So right-hand side, those are indistinguishable. Okay. All right. Now, who's in linear algebra? This is another example. This is a linear thing equal to itself. This is an example of an eigenvalue problem. I'll throw that out there. Daniel, you're in linear, right? Who else? Is anyone else in chat in linear? There you go. Tell Zachlin we mentioned this word today. I'll get bonus points with him. Zachlin has a spreadsheet of all the pluses and minuses. He keeps track of it. This is an example of an eigenvalue problem. Because you've got this great question. You've got this operator over here. You've got some operator over here. Let's call it L for linear operator. And we're putting a function into it. And we're getting the function back with an eigenvalue of 1. So this linear operator gives you the function back. So it's an eigenvalue. It's a multiple of itself. Yeah, isn't that cool? Yeah. I love linear algebra. Fun fact, linear algebra is the reason I became a math major. I was a minor at first because I was going to do physics and chemistry. And then I love linear algebra so much. However, that being said, Zachlin loves it more. He did his work in it. And he's the best person to have for that course. Okay, this example, I'll leave this to you to work through. The answer is there. What's the very first step, though, for this example? The very first step in all of these examples is to do what? Is you need to write in that standard form. Get the y prime by itself. So in this particular case, you would divide through by this quantity. You follow? So this would be your P of X. And so then to get your integrating factor, you'd be integrating this. Once again, not a big deal. A log pops up that you can cancel out more or less right away. And then that's your f of x. And there's your initial condition. Okay. So I'll leave the machinations to you. You've got the answer here. Of course, you can always ask about this. This would be like before you jump into the book homework, work on this first. If you have trouble with this one, just drop me an email. You can always send me a picture of your work and we'll see where you're going wrong. But that's the answer you should get. We're going to come back to this example in a couple of weeks when we do the applications. These are here. Once again, you can, if you want, go through these on your own to get these answers, but we will be revisiting this in a couple different contexts. The one I want to get to, we've got a few minutes left. I want to talk about this one. In your take-home, you will be verifying. In the take-home, you're going to start with the answer and do the calculus and algebra to check that this is the answer. But let's talk about this one because this involves one of these area as you go functions. So if I look at this equation, is it linear? I would have to put it in this form. In this particular case, the y prime is good to go, but I need to move the y over to the other side. Okay. And so the p of x here is minus 2x. So the integrating factor is e to the integral of minus 2x dx. And we suppress the constant. Okay? And so once again, it's an integrating factor. Factor means you multiply. So we're going to multiply the differential equation by this. It's called an integrating factor because it's going to turn the left-hand side into an exact differential. So here we go. And then 1. So now we're going to multiply both sides by that. And once again, I leave it to you in the privacy of your own home. Double check that the left-hand side is the exact derivative of e to the minus x squared y. And now all we got to do is what? To get rid of that derivative, we would integrate. Okay? And since we're running out of time, I'll do half the work for you. I'll do the left-hand side. And you can think about the right-hand side. And what do you think about the right-hand side? Yeah, it's a Gaussian integral. It cannot be done using the standard techniques you learn. You can bust out a power series, but we got a winter storm warning. We don't have time for that, or maybe we do have time for that. We'll be sitting doing nothing else. The point is that this is a non-elementary integral. So how do we handle this? All right. Well, we look at, first off, we're given an initial condition. Y at 2 is 4. So what we're going to do is we're going to express this antiderivative as one of these area as you go functions. So the upper limit of the integral will be x. We will be integrating e to the minus t squared dt. So we mentioned this in the video yesterday. This is an area as you go function. All right. And we're going to start, we can start at any value here because this function is continuous everywhere. We're going to start at x equals 2. Or rather t equals 2. Why? Because that's our initial condition. So when x is 2, y is 4. So if you think about, going back to Calc 1 now, the derivative of a function like this, courtesy of the fundamental theorem of calculus, is just going to be e to the minus x squared. That's exactly what we're trying to get here. You follow? Once again, why did I choose to integrate starting at 2? Because that's our initial condition, and you'll see why here in just a second. So that's the best we can do. So we got e to the minus x squared y equals the antiderivative of e to the minus x squared. Well, this is the one I'm using for that. Plus, of course, a what? Constant. Don't forget that constant. This is a particular antiderivative that captures them all. Now I just multiply by e to the x squared to get the y by itself. And this is one of your homework problems on the take-home. You're going to start with this, take the derivative, and show that it all works out. Now the question is, I got to figure out what that c is. And the way we find the c is we impose the initial condition. The initial condition, and this is why we picked 2, y at 2 is 4. So that means when x is 2, y is 4. You see why we picked starting at 2 here, because we're going to plug in x equals 2. So everywhere we see an x, we're going to plug in a 2. So there's going to be a 2 in there. That's going to get squared. We're going to plug a 2 in there. We're going to plug a 2 in there. That's going to get squared. And what's going to happen when we integrate from 2 to 2? Yeah, you're going to zero out. And so the integral's done, right? So we literally rigged things to work out in our favor. C e to the 2 squared, which is 4. So this integral, which we don't know how to do, it doesn't matter, because it's going to zero out. And now I can solve for c. You follow? And so my final answer for y equals I got all of this stuff. Plus my C. And since I've got the same base, I can go ahead and rewrite this as the x squared minus 4. Okay. So you just got to get used to this. If you didn't see this a lot in Calc 1, here it is again. Once again, if this is thrown, if you never saw this in Calc 1, let me know. I can send you a video, and because we do this kind of stuff in Calc 1 for your fundamental theorem. And so this is on your take-home. You're going to start with this and then verify it satisfies the initial condition, and then verify it satisfies the Diffie-Q. Okay. And once again, next week we've got existence and uniqueness for general, but we're going to focus mainly on proving this theorem. And when you get there's these types of things in linear algebra. When you get into the proofs in linear algebra, you're going to see the same sorts of techniques in linear algebra that you're going to see here in this proof. Okay, and there's your homework. Once again, the book has a nice LibGuide link. You can just go and work on the homework there, and they've got the answers there as well for you. You've got your take-home to be working on. Make sure you do your test 0. That's just the information sheet. That'll give you practice on downloading things and uploading things. But you need to turn that test 0 in by next Wednesday so I can record you as being present for the course. If you have questions on the take-home, let me know. Remember, the test and the take-home is gonna center around the section 1-2 stuff. So verifying solutions, not finding solutions, but verifying solutions, initial conditions and boundary conditions, and things like that. Okay? So we got a winter storm warning coming in. Be safe this weekend, folks. If you have any questions, feel free to shoot me an email. I do check my email a couple times a day over the weekend, or else you could always pop in early next week. All right? Thanks for coming, folks, and have a good weekend.